Alright, welcome everybody. So this video I'm going to talk to you about the Bohr model of the atom. And we're going to actually do a little bit more detail than I've done in the past. And I'm going to talk to you about a lot of the math that goes along with the Bohr model. And so in the last video we really focused on the quantization of light and how we have light as this particle and a wave. And what Bohr basically did was he applied this idea of quantized light to the atom, and he made the entire atom quantized. So, as it says here in the first slide, he used quantized energy to explain how charged particles, electrons, could orbit around the nucleus without losing any energy. A big issue with the models of the atoms up until that time was, how come the electron, which is negatively charged, isn't drawn into the nucleus? And so Bohr came up with this idea that the electrons were in stable orbits, and he dismissed the idea that they would be, pulled into the nucleus. And here are the main ideas of his model. So first he said that only models of certain radii, corresponding to certain definite energies, were permitted by an electron in the hydrogen atom. And so this is what we know as orbits. The electrons can orbit at certain distances from the nucleus. They will be stable. They will have that stable orbit. They won't lose or gain energy. The next is that the electron in a permitted orbit has specific energy, and no energy will be emitted. So that's what I just said. The electron's in this stable orbit, and it won't release, it won't absorb energy, it will just stay there. Something important about Bohr, which I want to bring up, is the idea that he was really focused on hydrogen. And all the mathematical calculations that he did, they worked exquisitely well for hydrogen. When we try to think of or try to apply Bohr's model and his mathematics to other elements that have more than one electron and more than one proton, the mathematics don't match up with what we observe experimentally. Now, what he also said was that energy is emitted or absorbed by an electron only as that electron changes from one energy level to another. And that energy that we see is given off as E equals h times the frequency. And this is what Planck and Einstein were using to describe the quantization of light. We see that the electron can emit these quantas, or these photons of energy, as the electron moves between energy states. So what was the data that Bohr was looking at that made it able for him to make this model? And he was looking at something called the bright line spectra. And so if you have an electron in these allowable energy states, what you would see is that when the electron moved between the energy states, it would give off these specific amounts of energy, and that those energies given off would have a certain color to them, or a wavelength. And so we would see what's known as line spectra. And this would be instead of a continuous spectra where it would just be a rainbow. So this is the hydrogen spectrum down here, and this is the sodium spectrum over there. You'll notice that the hydrogen has 4 different lines, and each one of those lines corresponds to where an electron moved from a higher energy state to a lower energy state. Specifically, this series of lines is called the Balmer Series. And the Balmer Series corresponds to these visible wavelengths when the electron returns back to the second energy level, n equals 2, as the final energy state. So we can look at Bohr's model as the following way here. We have these different energy levels. Here's energy level 1, energy level 2, 3, and so on. And depending on how the electron traveled between allowable energy states would determine the type of energy given off and the series of lines that we would see. And again, this is all for hydrogen right here. Bohr was studying hydrogen and hydrogen alone. Now, when we look at this, we see that these pink lines right here, which I'll highlight, all of these electrons return from an excited higher state back down to the first energy level, or energy level 1. We see that also there is electrons returning from a higher energy state back down to the second energy level. And we see that there's electrons returning back down to the third level. Each one of these transitions, as they're called, gives off a different amount of energy. And that different amount of energy corresponds to the spectral lines that we see. Now we'll do a lab with this, and you'll get to see what this actually looks like using equipment. We'll do antiquated equipment, and we'll do more modern day equipment. Now there's mathematics that are associated with this, and this is the mathematics that wasn't shown to you last year, but that I'm going to do with you this year. So what this shows me is that the change in energy, of an electron is equal to what's known as the Ryberg constant times 1 over the final energy level squared minus 1 over the initial energy level squared. What we can do is we can find this change in energy and then plug that into Planck's equation and find the wavelength. So let's try that. Let's do this for from 6 to 2. So from N6 to N2. So when I do this, I get negative 2.18 times 10 to the negative 18th times 1 over 2 squared, which is 4, minus 1 over 6 squared, which is 36. And if I go ahead and I actually do this in my calculator, let's see what I get here when I go ahead and I try this. So when I go ahead and I try this, I get 1 divided by 4 equals 0.25 minus, parentheses, 1 divided by 36. And I get a total of 0.222. And then I would then multiply that by the Ryberg constant, so times negative 2.18 times 10 to the negative 18th, and I get an energy change, a delta E, equal to 4.84 times 10 to the negative 19 joules. If I then take this and plug it into E equals H times C over lambda, and I solve for lambda, then I will get the following. I'll get the following value. So I will get Planck's constant 6.63 e to the negative 34th times the speed of light 3 e to the 8th divided by the energy that I just had 4.84 e to the negative 19th, and I will get for this something that is completely wrong. Let's try it one more time. 6.63 e to the negative 34th times, let's make sure I did that right, I did, times 3 e to the 8th, and then divided by 4.84 e to the 19th negative. And there we go. So for this, I get my wavelength is equal to 4.1 times 10 to the negative 7, which is 410 nanometers. So what we see from this, and I know that took a while to do, but what we see from this is that I get a line of a particular color. And if we scroll back up, we can see in the hydrogen spectrum, there it is, right around 410 nanometers, there's a line. That's the energy given off by an electron when it returns from the 6th state back down to the 2nd state or energy level. And you can see the series for the Bohr model here. When an electron returns back down to the 1st energy level, it gives off ultraviolet light, and that's called the Lyman series. When an electron returns back to the 2nd level, it gives off visible light, called the Balmer series. The Passion series, it will give off infrared radiation, and the bracket will be radio. And I guess the P fund would also be radio as too, but longer radio waves. So Bohr was successful in describing the hydrogen model of the atom. When he tried to apply this equation up here to other atoms, it didn't work properly, and he wasn't able to get the same exquisite detail, description, matching. Wow, this is, what the Balmer series is, and I've explained it mathematically. He didn't see that. This is for the hydrogen atom, and you can see these series of lines are well studied. So what we're going to do next is talk about the modern model of the atom, and I'll do that in my next video. Again, Bohr was limited to hydrogen. When he tried to explain his model for other atoms, he didn't see that same effect. His mathematics didn't work. So they needed a much more complicated model of the atom. It turns out the electron is a lot more complicated than we thought. The electron has this wave property to it. And so we'll talk about a de Broglie wavelength. We'll also talk about what the wave mechanical model is in the next video. Thanks so much for watching.